Great. Okay. It's my great pleasure to introduce Marco, who's going to talk to us today a little bit about statistics. Should be no surprise. Marco is a data science consultant and one of the main organizers of PyData, and I believe he's chairing PyData London this year. It's happening in about a month's time. A fantastic conference, so if you haven't got your ticket yet, you should definitely consider that. It's not too far away now. So with all of that, we'll get started. Over to you, Marco. Thank you.
Thank you. So yes, thanks for joining me today. I just want to tell you there are three types of lies. There are big lies, and there are statistics. So as a starting point, you can consider the following statement. In the Vatican City, there are 5.88 popes per square mile. And the number is correct. I'm not lying. I don't know much about the Vatican City per se, but I kind of feel that something funny is going on here. And that's the idea for the talk. Essentially, we are exposed to the use of statistics in different ways in everyday life, and statistics can be used to lie to us. So that's the topic of the talk. We're not going to talk about Python, even though we can do statistics in Python and advanced statistical modeling, but that's not the point. And the idea is that you, as the audience, simply want to be kind of a better citizen. You have an interest in statistics. You don't have to have any advanced kind of degree in a PhD in statistics or in math. So that's the idea for today. I'm going to start with correlation. So as a simple definition, correlation, if I give you a bit of an informal view first, it's already in the name. A couple of things that are happening together, so two things that are connected somehow. A bit more formally, correlation also gives you some sort of strength of the association between two variables. It's easier to think about linear correlation when you are first getting into it. So in linear correlation, the idea is that one variable is going up, the other variable is going up as well, and they kind of follow a line. That would be a positive correlation, or if a variable is going up, the other goes down again linearly. For example, to give you something a bit more concrete, when the temperature goes up, we sell more ice cream. Makes sense? Nicer weather, more people are eating ice cream. Now, you can see between ice cream and temperature that there is a connection. Intuitively, it makes sense. But when you look at the bigger picture, at all other possible examples of correlation, you don't always have a causation. You don't always have a cause and effect connection between two variables. So the phrase here, you will find it always referred to correlation does not imply causation. For example, talking again about ice cream, the more ice cream we sell, the more people are dying, drowning. So what is going on here? Is ice cream really a serial killer? There is something called a lurking variable. A lurking variable is a variable that is sort of looking at us, but we don't see it. And in the case of our ice cream sales example, the lurking variable again is temperature. So if the temperature goes up, more people go swimming, and therefore more people potentially can die drowning. At the same time, also more ice creams are being sold. So lurking variables is something that is there, but we all often don't notice it, we forget about it, or we just ignore it. One more example of lurking variable. When there is a fire incident, the more firefighters you deploy, the bigger the damage is. So you might say, well, let's deploy less firefighters so we keep the damage down. The lurking variable in this case is the severity of the incident. So when there is a big issue, more firefighters are deployed. But then, maybe politicians, when they do cuts to public services, they kind of look at the wrong variables. So when it comes to correlation and the notion of cause and effect, it's complicated. It could be that one is causing the other way around. Maybe there is a third variable involved. A and B together cause C, or C is the cause of A and B. Or maybe there is a transitive dependency, or maybe there is no dependency at all. So A and B simply correlate, but there is no connection. And just by looking at correlation, you can't really say if you have causation or not. Just to give you a few more examples, number of movies where you see Nicolas Cage as an actor, and number of people dying in a pool, falling into a pool. So those two variables correlate. So Nicolas Cage maybe bringing bad luck. Next, the consumption of margarine, also connected to violence. So murders by blunt object. Margarine makes you kind of aggressive. Now, easy to blame Facebook for everything nowadays, but if you look at the numbers, more Facebook users, bigger problems for Greece. So the national debt of Greece correlates with the number of users in Facebook. Internet Explorer, and again, violent crime. There's a nice correlation here. And finally, one of my favorite, if you look at the chocolate consumption per country and the number of Nobel Prizes per country, there's a nice linear correlation. So more chocolate means more Nobel Prizes. You see kind of Switzerland off the chart over there. And you notice a couple of nice outliers. So there's Sweden having more Nobel Prizes than expected. Who knows why? And Germany, for once, the Germans not very efficient. They consume more chocolate than they should compared to the number of Nobel Prizes. So there was a correlation. Next, I want to tell you what happens when you start slicing and dicing your data set. And what could happen is something called Simpson's paradox, which is a phenomenon firstly observed by someone whose name is not Simpson. So Simpson paradox, as a textbook example, I give you some numbers about the graduate school admissions in the 70s from Berkeley. You look at the total numbers and you look at the percentage of admissions, and essentially it's fair to ask whether there is some kind of gender bias, so the proportion of men is much higher compared to the proportion of women. So it's fair to ask the question. Then when you start slicing and dicing your data, you break down per department, for example, and you see a different story. Looking at the proportion of admissions on the women column, notice how for many, many departments, this proportion is much higher compared to the men's column. The thing is, when you look at the absolute numbers of applications, you see how men apply in big numbers for some departments, and in those departments they have a lower proportion of admissions. On the other side, women apply in low numbers when they have a high proportion of admissions. So there are a few interpretations here. Maybe women apply in big numbers for departments that are more challenging, or the other way around, men apply in big numbers for departments that are kind of easier to get in. Essentially, what is the problem here? The problem is that if you have any kind of agenda, you can show one part of the story or the other. And all these numbers are correct. They're just telling you a different story. So that was a Simpson paradox. Something else I want to mention is a sampling bias. So what is sampling? First, sampling is something we have to do nowadays in the age of big data. The idea is that we want to select a subset of data points of individuals from a bigger population with the idea of making some estimate about the broader population. And we want, of course, a subset of individuals that is representative of the whole population. What is bias? On the other side, bias, when we use bias in everyday language, it has a bit of a negative connotation because we associate bias with prejudice. Maybe there is some cultural influence going on. But in science, in statistics in particular, we talk about bias in a neutral fashion. It's just a systematic error. So when you put together sampling bias, we're talking about some kind of error that happened during sampling. So you didn't sample correctly. You don't have a representative subset of the population. As a classic example, a big headline back in the 40s, Dewey defeats Truman. So that's Truman, President Truman, the day he was elected president, and he's waving a newspaper with which is stating the opposite story. So what happened here? The newspaper from Chicago basically had to go off for the printer before they had the real numbers. And they simply trusted some kind of a phone survey that happened in the previous few days. But keep in mind this is 1948, so not everybody had a phone at home. And when you look at who can afford a phone, it's a specific subset of the population. So the people who picked up the phone to answer the phone survey, they were definitely not representative of the population in general. They were, kind of upper class, if you prefer, rich people at the time. And essentially, the survey was giving the completely wrong picture. And that's what happens when you don't sample you don't get a representative subset when you sample incorrectly. A particular case of sampling bias is also survivorship bias. Survivorship bias is what happens when you focus on the lottery winner and you forget about all the people who bought a lottery ticket without winning the lottery. So if you remember from the keynote this morning when Lucas mentioned, if I could do it, then you can do it as well. That's a classic kind of survivorship bias. So he went through explaining what happened, and he was very honest, saying, well, when you are successful, always it's by chance. And a couple of things could happen, and things can go in every sort of direction. But often when you read stories about, what do successful people have in common, that's, textbook survivorship bias. And if you look at successful people, if you consider being a billionaire a variable that determines your success, all these successful people, let's say Bill Gates, Steve Jobs, Zuckerberg, and so on, are all college dropouts. So should you stop your studies? Should you quit college? The nice thing about survivorship bias is that it works in both directions. So I didn't drop out of college, and I didn't become a billionaire. So that's survivorship bias. Next topic, data visualization. Why is data visualization important? Maybe you heard already the phrase, a picture is worth 1,000 words. Essentially, the idea is that you can use pictures to better convey insights on your data. And often, data visualization as a discipline will give you insights that you don't have just by doing some analysis on your data. Often, we talk about summary statistics when we look at new data. Here we have a common example with 4 different data sets, and they all have the same summary statistics. So if you pull the average value for X and Y, if you look at the standard deviation, if you look at the linear correlation, if you look at a few summary statistics, they are all the same. But then in the moment you plot the data, you will see a very different story. So that's why data visualization is important. You get insights that you wouldn't have otherwise. And you can use data visualization for storytelling to convey kind of complex topics in a simplified fashion. For example, here there is a picture about how different parties kind of agree with some sort of core decision. And the picture is showing how the Democrats, is based in the US, how the Democrats have a much, much higher proportion of agreement. And that's fine. But for some reason, the y-axis starts from 50 rather than starting from 0. So if you visualize the correct chart, the story is very different. Yes, the Democrats have a tiny higher proportion compared to the other columns, but they're kind of in the same ballpark. So depending on how you want to convey the message, you can simply cheat and cut the y-axis. Again, from the US, an example that is related to gun violence, of course, big topic in the US. In 2005, in Florida, they introduced a law called the Stand Your Ground Law. And they show that as soon as the law is introduced, there's kind of a drop in the chart of gun deaths. Again, look at the y-axis. It goes from 1,000, and it goes up to 0. So if you fix it, on the right-hand side is the fixed version. Reality is literally upside down. Another example, this one is from the Italian public TV service, the equivalent of the BBC, if you want. They have run a survey. They are asking, is the government friends with the lobby? Of course, being friends with the lobby is bad. So if you don't like the answer, 44% becomes a tiny slice. Luckily, I don't pay TV license anymore in Italy. So yeah, when I was living there, I was thinking, well, we are kind of world champion at this, until I moved to the UK. So this is from a few elections ago, a few leaflets from a variety of parties. There is no big red bus with fake numbers on it. But look at the numbers. This is from the conservatives. They're telling a story about how you shouldn't vote for the others, blah, blah, blah. According to the graphic designer of the Tories, 42% is much smaller than 32%. So that's one way of looking at it. The next one is from the Lib Dems. They are kind of close seconds. They are, it's one of those messages, yeah, go out and vote because we are close second and we need your vote to catch up. But then when you look at the real chart, well, they are second, but not very close. And for completeness, one more. This one is from the Labour Party. And in the UK, there's always this story about it's a race between two horses because first past the post system. And they say, don't waste your vote on the third little guy. You have to vote for us. So it is a race of two horses, although they literally forgot the second horse. That was the Green Party in this particular constituency. So yeah, I tried to make it across different parties to either to upset everybody or to make everybody happy. Next, I want to talk about significance, statistical significance, so a slightly more technical topic. The issue with statistical significance is one of the most unfortunate terms in statistics because in everyday life, when we talk about something as a significant event, we also consider it important. In statistics, we don't really have this idea of something significant being important as well. So when we look at statistically significant results, essentially we are simply a little bit more sure that the results are reliable, that they are not by chance. It doesn't mean that the results are important. It doesn't mean that the results are big. It doesn't mean that the results are even useful for any kind of decision process. Simply, we are a little bit more sure that they are not really random. But then, of course, when scientists report statistically significant results, then journalists can take the word significant and make a different story. Connected to the notion of statistical significance, we have this concept of p-values. It's one of those concepts that, when I was a student, I couldn't figure out the meaning of p-values. And now, many years later, I wish I could tell you that I fully understand p-values, but I don't. So I was trying to look it up, and there's even a big Wikipedia page of what the p-values are not. So if you don't understand p-values, you're not alone. So let's try to figure out what p-values are. Essentially, it's about probabilities of observing our results when the null hypothesis is true. We're talking about probability, not certainty. And more importantly, typically in publications, you will see a p-value set to some kind of arbitrary threshold that often is 0.05. Some fields are a little bit more strict, others are a little bit more relaxed. Essentially, it's a probability about being a little bit more sure that what we see is not randomness. It doesn't tell us anything else. Related to the notion of p-values, we have a practice called data dredging. That's dredging. When we talk about data dredging, also called p-hacking or data fishing, essentially we are looking for significance before testing, before having any hypothesis. The convention should be we formulate some hypothesis, we collect data, and we prove or disprove the hypothesis. Often people try to simply brute force the data that they have, and they look for something that is statistically significant, and they come up with an hypothesis in retrospective. So the idea is if you're looking for patterns, you are doing some exploratory analysis, that's fine, but testing the hypothesis backtesting your hypothesis on the same data set is not, because you are going to confirm what you already saw. And that's kind of like cheating. So that was statistical significance, a slightly more technical topic. One more thing, a little bit of a bonus content. Celebrities on Twitter. This could be, a talk on its own, talk of many, many hours. You have celebrities talking about things they don't understand on Twitter and coming up with strong statements. And I could be lazy and pick up any kind of celebrity and I would find something. Here I went for Bill Gates, who is doing a lot of work nowadays in terms of charity and fighting malaria and humanitarian work. And talking about his work, basically he's trying to make a point here about how mosquitoes are dangerous. And he's reporting some numbers about number of people who die when they encounter a shark. It's a relatively small number compared to deaths from mosquitoes. Those are raw numbers, and that's fine. The point is, well, again, we're looking at numbers, but what is the cause? So the conditional probabilities are, of course, different. I never encountered a shark in my life, but I've encountered many, many mosquitoes. So you see the picture here is reported as if mosquitoes are terrible. Of course, they are the cause of malaria, and he's focusing on that at the moment. But the condition that we are looking at is something completely different. So wrapping up, I gave you a few examples of lies and big lies and something done on purpose or something done by mistake. So it feels like we are screwed. Essentially, everybody lies. Now, the point of the talk is not to create like a new generation of conspiracists or anything like that. The point of the talk is simply to make clear that this kind of problems can happen to everybody. And we as citizens, in the general case, and as specialized users, some of us are data analysts, some of us are data scientists, some of us may have some kind of more formal training in statistics, other less. The idea is that it's important to ask questions and to make a clear distinction between what is good science versus big, loud headlines. And as I said, nobody is immune to this. It could happen by mistake to everybody. So it's always important to ask questions. For example, what is the context? What is the bigger picture? Who's paying for a particular study? Is there anything that is not being reported? Is there anything missing? And all in all, so what? You see some numbers, you see some statistics, so what? You should put things in context. So that's the end for me. Thanks for sticking around. I just want to mention, Alex mentioned it already, I'm part of the organization committee for PyData London. So if you want to listen to people who know about statistics and data science and machine learning and data engineering and all the stuff, next month we will be down the road near Tower Bridge with a 3-day conference. Thank you very much.
We have 2 minutes for questions. You're close.
Thank you. That was great. That was really funny. Unfortunately, we live in a world where the truth doesn't matter as much as important people saying stuff. And we have the benefit of being in this lovely room and listening to these cool talks. And there are millions of people not in this room listening to this cool talk who think, for example, that £350 million a week is a reasonable sounding number. So what more can we do other than just be informed and just us knowing about this?
Yeah, that's a huge question. So the opposite of ignorance is probably education. So that's my starting point. And of course, money always wins against education and good intention. So I don't have any short-term or long-term plan, but I would say yes, education and carry on with education is kind of the reasonable, good citizenship type of thing. In terms of making big statements, then there is always the issue that there are parts of society that should be held accountable by some other parts of society. So when there is a politician making a wrong statement, wrong as in reporting wrong numbers on purpose, there should be a journalist asking the question. It's not happening every time, it's happening less and less nowadays. And with what we experience online, with the freemium model, so free content, but advertisement pay for it, it's much easier to publish extreme views, extreme polarizing content, if you want, than it is to have a proper, in-depth analysis on whatever issue you're discussing, proposing mild views and suggestions. So, yeah, it looks like we're screwed.
Another question.
How can I get better at lying with statistics?
Yeah, that's not kind of the point of my talk. I guess, if you have an agenda, you can always twist the table and propose correct numbers that are suggesting that your story is correct and pretending to ignore the numbers that are not supporting your point. That's what people do all the time, right? So is omission really a lie? Well, it depends on the context again.
I think you just need more Twitter followers.
Yeah.
Thank you very much, Marco. We're out of time for questions, but I'm sure the
You can take them
discussion
offline. Yeah.
can carry on. Thank you very much.
Thank you.